So good morning and welcome back. After the last lecture, some of you asked me about representations of Lie algebras and Lie groups. And I decided to have a brief section on this because indeed, mostly you meet Lie algebras and Lie groups in physics in terms of their representations, and very often they're even defined in terms of their representations. This is something we didn't do. We defined a Lie group as a smooth manifold with a group law that is compatible with the smooth structure, and we defined the Lie algebra as the left invariant vector fields, and of course we could pull all of this back to the tangent space at the identity with a suitably induced bracket. But what on earth are these representations? So we should comment on that because it's very important. So we have a section 4.6, linear representations of Lie algebras and Lie groups. And we start with the algebras, and then we briefly comment on the groups. Now again, you can give at least half semester long lecture on this topic, so I'll present mainly no proofs, but I'll introduce the important concepts. So the key concept is the following. Definition: let L with our abstract Lie bracket be a Lie algebra. Then a representation of this Lie algebra is the following. It is a linear map which we may call rho. So let's say a representation rho of this algebra, this Lie algebra is a linear map rho that goes from L. Why can I say linear? Well, because L in particular is a vector space, goes into the endomorphisms of some vector space V. So this is some vector space V over the real or the complex numbers, such that, okay, does that make sense? Well, if V is a vector space, let's say some finite dimensional vector space, and then we have a finite dimensional representation. Does that make sense? Well, L is a vector space, yeah, and V, well, that's a vector space because that's all the linear maps from V to V, which by themselves constitute a vector space again, such that, well, we need somehow compatibility with the Lie algebra bracket, such that, well, I can first take the bracket of two Lie algebra elements, let's call them A and B, and then the result will be a Lie algebra element, and I map it, and I require that this be the same as first mapping one of them and mapping the other of them, and then the result being put into brackets. These are now, of course, not the differential geometric brackets because these are not vector fields, they're just endomorphisms on V, and where this bracket is defined, so this is defined as, whenever we write this, now we mean this is an endomorphism, this is an endomorphism, so what I can certainly do, I can execute one after the other. I can compose them, and then I can again compose them, but in the opposite order, and that's of course what we know as a commutator. You take this and apply it to this, minus this applied to this. This is of course again an endomorphism, so this bracket here is a bilinear map from V and end V into end V. That is, the bracket here goes from end V cross end V into end V. And of course, it's bilinear, it's easily checked. And in fact, by construction, it's antisymmetric. And you can also check that it satisfies the Jacobi identity. Aha, that means why do I map into the endomorphisms? Well, because the endomorphisms, by virtue of having a natural composition on them, can be immediately made into a Lie algebra. Okay? So, and what I formulated here is that I say a representation of an abstract Lie algebra is a linear mapping into NV, which itself carries a Lie bracket, namely this commutator bracket, and I require compatibility that I can first take the bracket and then map, or I can map the elements and then take the bracket, and should be the same outcome. Okay? And so the this rho is then called the representation, and the vector space, the particular vector space that we used here, the particular vector space V that comes with a representation is called the representation space. The representation space. Okay, so that is maybe confusing because one might have thought, well, you map the Lie algebra to NV, so you might say NV is the representation space where you represent the L. Well, that is what it is, but the terminology says this V is the representation space. Okay? And the idea behind it is that once you have a row of some Lie algebra element, some row of A, you can act on the representation space V, because a row of A, of a little a, is an endomorphism in V, so an endomorphism can act on a vector and produce a new vector. That's the idea. Okay, so that's the abstract definition of a linear representation, so we should call this then a linear representation, because we do this by endomorphisms on a vector space. Okay, so example or examples. Well, so we discussed at great length the SL2C Lie algebra, and we found that it has three generators, well, three basis vectors. This is three-dimensional algebra, and we wrote down these commutation relations for it. This was 2x2, this is x1, x3 is minus 2x3, and this is x2, x3 is x1, and we derived this from the left invariant vector fields, and this structure was inherited, after all, from the product structure on the Lie group, capital SL2C. But this is a Lie algebra, and now these three vector fields, these three vectors, we had only the interpretation, these are the representatives of the left invariant vector fields at the identity. We didn't know more. Now a representation, because there in general, there are many, many representations. A representation of SL2C is provided by so let's call it rho, and it takes the first Lie algebra basis vector. Because it's a linear map, it suffices to prescribe it on a basis, right? So I prescribe it on a basis. I say this one is 1, minus 1, 0, 0. On the second one, it's 0, 1, 0, 0. And rho on the third one is 0, 0, 1, 0. So what I'm obviously doing here, I'm providing a representation SL2C, which chooses as its representation space, let's say, C2. And obviously, I can give elements in C2 with respect to a canonical basis, because this is a C cross C I'm acting on. I can represent linear maps, endomorphisms, by their representing matrices, and I choose these. Now, this is a linear map, all right, well, by linear extension, of course, continuation. But now check whether this satisfies this compatibility condition. Well, we can calculate what is rho of x1 commutator rho of x2, for instance. So let's take these two guys. I have to take the commutator, and that's, of course, the composition here in the abstract in the abstract writing, of course, corresponds to matrix multiplication once I take these basis representations. And so I have to calculate 1, 0, 0, minus 1 on 0, 1, 0, 0, minus 0, 1, 0, 0 on 1, 0, 0, minus 1 using the infamous matrix multiplication. And that yields 0, there's a 1 here, 0 here, and 0 here, minus, okay, what does this yield? 0 here, minus 1 here, 0, 0. So this is equal to 2 times 0, 1, 0, 0. But 2 times 0, 1, 0, 0 is 2 times rho of x2, right? And 2 times rho of x2, but this x2, so this is, of course, because rho is linear, this is rho times 2x2, because of the linearity of rho, but that is rho of the commutator of x1 with x2, because x1 with x2 is 2x2, and so we see that for the pair x1, x2, this relation here, this compatibility condition, is satisfied. Why? So now I also check this for 1 and 3 and 2 and 3. And if for all of these it's valid, it's already valid for any elements of the Lie algebra because the bracket is bilinear, so I only need to check this on a basis. Okay? So yeah, that's right. This is a representation of SL2C, this kind of matrix representation. Okay? And that is how it's usually given. And then you can ask, well, if that is so what is rho of SL2C? So the entire image, so that lies in end C squared. Okay? But if you now think about the rho of all of this is, of course, the vector space generated by these three, and that's, of course, the vector space of matrices alpha, beta, gamma, delta, where alpha plus delta equals 0. Or more abstractly written, it's the space of all endomorphisms here that have trace 0. They're the trace-free matrices. And that's what it's usually said. It says SL2C, the group, is the matrices of determinant 1, and the corresponding algebra is the 2 by 2 matrices that are trace-free. But in fact, this is just a statement on the representations of the group and the algebra. Didn't tell you what a group representation is. We'll come to that later. But usually one defines the algebra this way. But we didn't, because we come from the group, we went the abstract way, and this is just one representation. And the whole business about representations is that for any given Lie algebra, well, certain conditions apply, you have several representations. There's not one representation, and this is just a representation here. Okay. Now, a representation that, of course, appears in physics very often, or an algebra that appears in physics very often, is the rotation algebra. So this was the first example, A. And let's have an example, B. You can have L be SO3R. So the rotations, well, that's the idea. That's the Lie algebra that comes from the rotation group here. And, well, should I take this? Or I take this one. And it's defined like any Lie algebra. I can define it by saying there is some basis. It's a three-dimensional Lie algebra, so SO3, R happens to be three-dimensional, and so it has a basis, and I and j run from 1 to 3, and the statement is there is a basis where the structure coefficients, which I always have, so I always have these guys, and now I need to determine these guys, and I do this as follows. First, I define the killing form. That's KAB is CA, CB, MN, NM. We had this before. And then using the killing form, I pull down this index. I define C down Kij. What is this? I don't know, because I only know what C up Kij is. Well, I define it to be CKM, CMIJ. So one could say I pull the index, but well, that's just a way of saying this. So you can do this also coordinate free, but anyway, let's do it like this, or basis free. So this is then this guy, and the SO31 is now defined by 3R is defined by having these C's with the indices down Kij to be epsilon ijk. Well, what that means is that is 1 if ijk is an even permutation of 1, 2, 3. It's -1 if this is an odd permutation of 1, 2, 3, and it's 0 else. If it's no permutation at all, for instance, 1, 1, 2. So if you have these totally antisymmetric structure coefficients, but in order to be able to say they're totally antisymmetric, you need to have the killing form to pull this down. Okay? And of course, you can reconstruct this, and you can think, if you have this, how do you get back this guy? And so you construct this from this epsilon. Okay, so that's SO3R. So the question is, are we able to actually find a representation for SO3R? And again, a representation is given by rho taking SO3, R linearly into the endomorphisms over R3. That is what you learn in elementary school, that the rotation algebra can act, the three-dimensional rotation algebra can act on R3. And in fact, you do something like rho of x1 is 1 minus 1, 0, 0, 0, 0, 0, 0, 0. Rho of x2 is, so now it could be that I start being inconsistent in my choice of signs. I think there the sign choice is the other way around. So here it's plus minus, and here it's minus plus, but I'm not entirely sure. You should check for yourself, but up to signs, this is right. So 0, 0, 0, 0, 0, 0, let's say it's here again like this. And please check whether it's right with the signs, and you can start checking whether, again, this compatibility condition that the Lie bracket is respected in the above sense is satisfied. So this is also a representation of SO3R. But as you famously know from quantum mechanics, there is another representation, right? So another representation of SO3, R is rho, let's call it rho spin. And what does that do? Well, it takes elements of SO3, R, and it maps them linearly to the endomorphisms over C squared. So it acts on two-component complex objects, right? Two complex component objects. And there it's something like rho spin takes, again, the first basis element, if the basis is given such that these are the algebra relations, And so now there is an issue of whether you get there an I or you don't get an I. So it's something like 1/2 sigma 1 matrix, 1/2 the sigma 2 matrix, and 1/2 the sigma 3 matrix. And don't kill me if you need an overall I. Please figure this out for yourself as well. And again, the sigma matrices, they also commute like this, maybe plus or minus, including a factor of I or not. And that's another representation of the rotation algebra. So you have the rotation algebra, so that's the algebra of the rotation group in 3 dimensions. And you can represent this on R3. You can rotate stuff in 3 space, in real 3 space, or you can represent the same algebra on C2, and these are, of course, the spinners you'd use in Schrödinger theory, right? And so they're transformed under the same symmetry algebra or algebra. Okay, so these are different representations. Okay, so here I gave you a second one. Maybe it's worth giving a third example. Well, it's definitely worth giving a third example, and the fourth one. So the third example, so this one I gave because we know all the background, the SL2C one. The SO3 one I gave because you know it from physics anyway. There's another one you know anyway, and that is there is always the trivial representation on any vector space as the representation space. Although, so if you have a Lie algebra, you can always give rho trivial that takes the algebra linearly in the endomorphisms over some vector space, but every element A is simply being mapped to the 0 map on these endomorphisms, so on the matrix with only zeros, if you wish. This is, of course, a representation because a row of the commutator of A and B, not the commutator, a row of the Lie bracket, well, whatever it is, it will be sent to 0, and row of A, row of B with the commutator on the endomorphisms, well, if each of these is 0, then this will, of course, be 0, and that's the same 0, because this is the 0 in the endomorphisms, and this is also the 0 in the endomorphisms. So that's always the same, so compatibility is always there, and physicists call this the scalar representation. Scalar here in the sense that nothing changes under, well, because the algebra. We come to that later. Anyway, that's the trivial representation. And there is another representation we used all the time during the last few lectures, but we never called it a representation. And it answered the question, so every Lie algebra has a trivial representation. Question, does every Lie algebra have a non-trivial representation? Have a non-trivial representation? And I also introduced the notion of a faithful representation in a second. And the answer is yes. What you can do, you take a row and you call this the adjoint representation. Does the following. That's the representation that takes the Lie algebra and linearly maps it into an endomorphism space. And you already got the heck of it. What is one choice you make for a representation is the choice on which space, what representation spaces you choose. The other choice, once you have chosen a representation space, there may still be different linear maps, right? And these are then representations on the same representation space, but they could still be different maps. It's clear, if you chose the target, you haven't chosen the whole thing yet. Okay, but anyway, so one choice is choosing the representation space, and you want to represent a linear algebra. Now imagine you're very short of examples for vector spaces. Well, one vector space I already gave you, namely the vector space underlying the Lie algebra. So it's an interesting question to ask, is it possible to represent the Lie algebra on the representation space that's given by the Lie algebra itself? So you're not a problem. I think okay, so we choose this as the representation space, and the question is, how do we construct a Lie algebra there? And I already showed you how, namely, you take an element here, and you map it to A, comma, well, this Lie bracket A, comma, open slot. What does that mean? Well, this guy we called add of A. So the add map we had all the time does nothing but it takes an element from the Lie algebra and sends it to a linear map from the Lie algebra to the Lie algebra, because this guy, if I feed it an element L of the Lie algebra, it sends this to A comma L, which is again an element of the Lie algebra. So add A is an endomorphism on L, right? So it's the adjoint representation. Yes, the adjoint representation, okay? And you see that our classification of semi-simple and finally simple Lie algebras made essential use of the adjoint representation, because we took these guys, add, and we on the Cartan subalgebra, we said all the others are eigenvectors and so on, okay? So this is the adjoint representation. So now, if we want to study representations, again, we want to study building blocks. So if we have a representation that can be understood by understanding two other representations, we don't need to bother about this representation. We can understand in terms of others. And so the key definition is a representation rho of L into some and V of a Lie algebra is called reducible. So it can be decomposed into pieces, is called reducible if there exists a vector subspace of the representation space. So let's call it U, a vector subspace U of the representation space, such that applying rho for any Lie algebra element A to an element U of that subspace, so such that for all A in L and for all U only in the subspace, the result of this action again lies only in that subspace. So in other words, you can restrict this map. So in other words, the representation map rho restricts to rho sub U, which is a map from only from all of L only into end of U. Yeah, that's right. Only into end of U, and this is still a linear map, okay? And the point is, if such a non-trivial, it exists a subvector space that's non-zero. This is not the zero vector space, because that for that one, it of course always works. Then we call the representation reducible, and otherwise the representation is called irreducible. Otherwise, rho taking L into NV is called irreducible. So let me provide an example for that. So we saw we had the row that took SO3, R into the endomorphisms over R3, with the row of x1, x2, and x3 being defined as I did. Okay? And we also had the representation row spin. Well, we could call this row vector, right? And we call this row spin that takes the same Lie algebra into endomorphisms on C2. So that can act then, the results can act on spinners in Schrödinger theory, say. Now, of course, we could construct a representation that we now call rows. So this was row vec and row spin. And we could construct a row that is SO3, R, and that sends it to the endomorphisms. Okay, I hope I didn't get into trouble here with the endomorphisms. Yeah, I think that's fine. Into the endomorphisms over R3 plus C2. Okay. So the idea is that now I say a row of still just some element from here is being mapped to, now I give you the representing matrix of this guy, is being mapped to row vec of A. That's a 3 by 3 real matrix. And here I go to row spin of A. And that's a 2 by 2 complex matrix, whatever. The whole thing can be considered as a complex matrix. And there are zeros here. I can definitely do that. And if you now ask about the commutation behavior of two objects of this form, it's clear the matrix multiplication can be executed blockwise, right? That means if I start commutating these guys, this guy will only see the relevant block in the other row of B, and this guy will only see the relevant block in the row of B. And of course, this is again representation. If this is a representation and this is a representation, and I have this of this block form, then it can immediately be checked that rho is again a representation. Okay? But now, U equals R3, namely this part of R3, and U prime equal C squared, namely this part, and the others being set to 0. So I should write here plus nothing. Well, you know what I mean by this. Are subspaces, are vector subspaces of this vector space. Okay? They're vector subspaces, and indeed, if I act only on a vector, you have to think about think about this thing acts on a vector that has only entries up here and 2 zeros here. That's of course an element in this subspace. If you act on this, again blockwise, the result will again lie in here. There will, from these 3 stars, there will nothing put here because of this block structure. So this R3 here, the subspace, is what you call an invariant subspace. Well, I didn't call it like this. There exists a vector subspace U called an invariant subspace, such that action on there produces a result still in there. And the same here. So we see immediately, if it has this block form, then the representation is reducible. Okay? And one can also show that these two representations are not reducible. And I can always, if I have a reducible representation, I can always understand it. This is just an example. I can always understand it by the building blocks, which are reducible representations. And then, of course, I only use these building blocks. Now, in particle physics, people say particles are irreducible representations of the underlying symmetry group. So let's say you take a particle, well, the symmetry group of classical mechanics is the Galilei group. So you have to bother not only about rotations, but also about Galilei boosts, and also about translations in space-time. Well, that's yeah, okay, fine. But that's a little complicated. Let's take the symmetry group of a particle that I trap at some point. So I trap a particle in a certain place, but then the particle, there's still rotational invariance, right? You cannot move it, but it's still rotational invariance. And so that would be a particle that has an SO3 group, capital SO3 rotation group invariance. This is the corresponding algebra. And if you say particles are representations of that group, you can see if you trap a particle, then one representation is to represent it by a vector, the other one is by a scalar, but one representation is to represent it by a two-component spinner. And that's, of course, what you do in quantum mechanics. But you could now, if you said a particle is an irreducible representation of the symmetry algebra in this case, if you took a reducible one, you could always make two particles out of it. Okay? So two particles also transform according to the symmetry and some representation, but you want to understand that an elementary particle is only an irreducible representation. Okay? You can understand, you can study the elementary particle on its own. You don't, if you always have to study a particle together with another particle, well, then neither of them is elementary, then the whole thing is maybe elementary, right? So that's the, well, I'm just talking about why this term irreducible representation comes up in particle physics. You want to understand the elementary building blocks. In physics, you call that elementary particle. Okay. Question to reducibility, yeah? Yeah. A non-trivial, I should have written, non-trivial, and you're right, it's not, it doesn't suffice to exclude the zero, you need to exclude the entire space too, because otherwise, yeah, that's right, thank you, that's right. Okay, good. There's yet another definition one uses quite frequently, and that is a representation rho L into n over some representation space V is called faithful if rho is injective. So one Lie algebra element under the map rho doesn't hit the same endomorphism twice. Okay? Yeah. Yeah, that's right. Doesn't hit the same endomorphism. No, what did I say? So you know that injective means that if you have equal images, you had equal guys here. So no two here hit the same there. That's it. No two here hit the same here under the map rho. So it's the lover's map, and then you understand faithful. It's injective. Okay. So you could check whether the adjoint representation, for instance, is injective. And you could check whether the adjoint representation is irreducible. Okay. Well, let's formulate this as a homework problem. So let's say problem sheet. Check irreducibility and faithfulness of rho equals ad of the adjoint representation. Now, there's a very important concept in the study of representations, and that's the concept of a so-called Casimir operator. And because in physics very often you are handed the Lie algebra already in a representation, there's sometimes some confusion that you can construct a Casimir operator for a given Lie algebra, but that's not true. The Casimir operator can be constructed for a given representation of a given Lie algebra. Casimir operator can be constructed for any given representation of any given Lie algebra. Okay, how can we do this? Well, this proceeds in several steps. So I all subsume this under the definition of Casimir operator, but fine. So the first thing we can do, of course, if we have a representation rho of our Lie algebra on some representation space, we can define the killing form on end V with the commutator bracket. Because after all, end V equipped with the commutator bracket is a Lie algebra, so I can definitely define the killing form on there, and that would be the killing form, and I put k down rho because it has to do with a particular representation, k down rho of, okay, how do you call this? Up over here, the endomorphisms, I don't know, call them phi and psi, okay, is defined as usual. Hang on a second. No, I want to do this differently. No, I want to do this differently. I'm sorry. So it's obvious you can define the killing form on end V with the bracket because that's a Lie algebra. But I want to do something different. I want to define a new killing form on L. But now it's the rho killing form, and I call it k rho. It takes two elements of L, and it still sends them to, well, say the complex numbers in case of a complex Lie algebra. But now it's defined as k rho takes an A and a B in the Lie algebra and sends them to the trace of, and now it comes, of rho of A circ rho of B. And you see that that the killing form we defined so far, so hence the killing form we had so far was the killing form with respect to the adjoint representation. So as we previously defined it, because there we put here add A circ add B. Okay? But you can of course define this k rho for any representation. Okay? So, well, that's the first thing. That has nothing to do with the well, it has to do with the Casimir operator, but so you have that. Now you define the Casimir operator. So that's step B. You define the Casimir operator, let's call it omega, with respect to the given representation as, well, what is it? It's a map from V to V. So it's an element in end V. And it's defined as omega rho. Hold on a second. Yes, omega rho is defined as the sum I equals 1 to the dimension of the Lie algebra, and you take the rho of xi. Xi is a basis, I'll write this down in a second, of the Lie algebra, after rho of xi I. What on earth is xi I? Well, because it's eaten by the row, this must be in the Lie algebra, and this must be in the Lie algebra too, where x1 to x dim L is any basis, it doesn't matter which one, is any basis of L, okay? And xi1 to xi dim L is the other basis of L for which we use our newly defined k-row killing form, k-row, for which k-row of xi, comma xi j, you see it eats another set of vectors on L, is delta ij, which with two indices down looks funny, but it's 1 for I equals j and 0 else. Okay. So the idea here is what I could also do, I could use xi's here, and I could again use the xi's, but then I need to orthonormalize the basis of the Lie algebra with respect to the killing form. Okay? And as it's written down here, I could only find an orthonormal basis if the Lie group I come from is compact, and then I probably have to put a minus here, -1 or something. Yeah. Let me think for a second. Yeah, so this actually this only works if the Lie group is compact, because otherwise I don't find such a basis. Okay, so for compact groups it works like this. Now, okay, you have this, and this here is the so-called Casimir operator, and obviously you can feed it a vector in the representation space, and it munches it through, it kicks out a vector in the representation space, and we have the theorem, and I asked you to prove that on the problem sheet, that if you take the row omega row, this is an element of NV as we just saw, and you take any other, the row of any other Lie algebra element A, so that the whole thing is again in NV, then you can of course calculate the commutator of these two, and you will always get 0. So the motto here is that the Casimir operator commutes with everything. Well, everything meaning every image with the whole row of L. So everything is row of L. Okay? And this is how it's often introduced. Okay? So now about objects like this, there is something called Schur's lemma. Okay? And that states in this particular context that if rho is irreducible, but that we can always do because we can always study the irreducible parts of a representation. If rho is irreducible, then the omega rho is always equal to some number C that depends on rho. So this is just an element, this is just a number. Well, I say it's an element of C, or it could also be an element of R. It depends on over what vector space you are, times the identity on the representation space. Or if you would express it in terms of a matrix, it would be a diagonal matrix with 0, 0, 0, 0, 0 on the diagonal. That's Schur's lemma. But this only is true if rho is irreducible. Okay. So the Casimir operator of an irreducible representation is actually a constant multiple of the identity on the representation space. Now let us try to show. Let's try to show the following claim: that this number C rho is always given in the irreducible case by the dimension of the Lie algebra divided by the dimension of the representation space. Okay, so if you ask what's okay, let's try to show this. So proof. Let's see how this can be done. Aha. Right. So if rho irreducible, it follows that omega rho is C rho times the identity on V. And that means that the trace of omega rho is an endomorphism on V, so I can take the trace, is the trace of C rho times id V, but the trace is R linear, so this is C rho or C linear times the trace of id V. And what is the trace of the identity map on the vector space? I hear? The dimension of the vector space. That's right. It's 0 times dim V. Aha. So this dim V, we apparently get somehow from here. Okay, that looks good because we have a 0 times dim V. We could take this here. So what we have to show that the trace of omega rho has something to do with the dimension of L here, I guess. Okay, so let's write down what that is. So the trace of omega rho is the trace of, what was omega rho? Was the sum from I equals 1 to the dimension of L, aha, starts looking good, rho of xi after rho of xi I. Okay? Ah, okay, so now let's pull out the sum, dim L, and we just have the trace of rho of xi after rho of xi I. But this is nothing but our killing form k rho with respect to the rho map of xi comma xi I. Do you agree? But the xi i's were chosen exactly such that this is delta, that this is always 1. Right? For every I, this is 1, because I is a delta ij, is a 1. So we have the sum over I equals 1 to dim L over 1, and that very nicely is dim L. So dim L is C rho times dim V, so C rho is dim L by dim V. Okay, good. So that comes out. And what does it mean? Well, it means that if I have different representation spaces for the same, two representation spaces V1 and V2 for the same Lie algebra, they are labeled by this factor C rho that defines, for an irreducible representation, defines the Casimir operator. Okay, so in other words, I can act with the Casimir operator on any element in the vector space V of this one particular representation space, and I'll get the same number. Okay? And well, if you do this in physics, you know that if you act with, so example, but now we've got to be careful because in physics we're choosing different factors here, but the example in spirit is you have ji, jj equals epsilon ij, kjk, okay, something of that type. So this just being considered numerically are the commutation relations, so abstract Lie algebra. So this is the SO3R rotation group. And then you can, of course, take this rho spin, okay, take rho spin, and take it of any of the j's. Well, it doesn't matter, the ith one. And so J1, J2, J3. And then you can define what usually in physics you call J vector squared. But it's not J vector squared. It's the rho of the Ji squared. So you take rho of Ji times rho of Ji, and you sum I equals 1, 2, 3. And you see, now in principle, if you do this, then you claim these are the x's, and these are the j's, the xi's as well. Well, you've got to be careful that you have the right normalization here, and I think you don't. I think you need a factor 1/2 or something in front. Yeah, I think that's right. Not entirely sure. Something like this, okay? And this you call the rho, omega rho, yeah, the omega rho. And now if you choose here, you can take omega rho vector, and then you can take the sum, say it's 1/2, and then you take this times this, so you take the square of every individual one. So how is that? That's the 1 minus 1, 0, 0, 0, 0, 0, 0, 0 squared. No, it's this composition with itself, goes into matrix multiplication, plus this squared, squared, squared. No, these three, what does it give? It's 1/2. And it yields 1, 1, 0 for this first one. You agree? And for the second one we defined, it yields 1, 0, 1. And for the third j we defined in the vector representation, it yields 0, 1, 1. Agree? Because there are always these 1 minus 1 blocks and everything else is 0. You get this. So what do you have? You have 1/2 times 2, 2, 2. Equals 1, 1, 1. 1, 1, 1, 1, 1. And this is a particular example. So the C rho vector times 1, 1, 1. The number for the vector representation C is 1. Agree? So I should have written this 1/2 here. So these are the xi's, okay? So you go here, and the rho vec we just calculated for a particular representation. We calculated this Casimir operator, and gives the C rho vec times the identity. That means, so from here we learn, C rho in the vector representation is 1. Does this work with our theorem? Oh yeah, the three-dimensional rotation algebra divided by the dimension of the vector representation. The representation space is R3, is 3 divided by 3 is 1. Aha, wonderful. So again, usually in physics, we don't have the factor 1/2, and then everything is wrong by a factor 1/2. But I need to make sure that this is the, if you want, dual other basis with respect to the killing form once you've chosen this basis. Yeah? Oh, yeah. Where? This one. So we believe that without the square, this is rho of J1 in the vector representation. And now I take the, oh, I see. Okay, yeah, because this is an I. This is like a complex I, this block, and it's a minus sign. Aha. But didn't I always say that I have a problem with the minus sign over there, where I said it only works for compact groups, but if I want to have it work for compact groups, I know that the k row of the xi, xi j, I want to have to be delta ij. For compact groups, I can only achieve, for compact groups, the killing form would be negative definite, so I should have a minus sign here. So that means I should have an overall minus sign here in the definition, and then the signs are right. Okay, so I apologize for the signs, but it's excellent that you see this. Okay, thank you. All right, but so now let's not miss out, but I need your help with the sigma matrices. Let's not miss out on the next example, which is again the abstract rotation group, epsilon ij kj k. But now we take not the vector representation, so I here wrote rho spin. Well, I have rho spin, I have rho vec. And then we evaluated it for rho vec. Now for rho spin, we said the ith one is represented by the ith sigma matrix 1/2. And can you remind me of the sigma matrices? This is embarrassing, but sigma matrices? 0, 1, 1, 0. Yeah. Yeah, okay, thank you very much. Okay, so let's very quickly check sigma 1 with sigma 2, how that works. 0, 1, 1, 0 times, I'm after a factor here, so I need to check this, minus I 0. That yields I 0, 0, minus I. And so this is I times sigma 3. Aha, exactly. And now the opposite is 0 minus I 0 on 0, 1, 1, 0 equals minus I 0, 0, I, and that is minus I sigma 3. So that means the commutator, and that's really the commutator, of sigma 1 with sigma 2 yields 2 times I sigma 3, because this minus goes by the minus from this bracket. And so the sigma 3 is good because 1, 2, 3, there's a 1, but I have a factor of 2i that I don't like. So therefore, I take sigma half matrices. That gives me an overall factor of 1/4, right, compared to what I had. But this is overall factor of 1/2, so that's sigma 3/2. So if instead of sigma matrices, I take sigma half matrices, I have the unit factor, and that's why I chose the half here. But there's a remaining problem, that is I have an I here. So that means, however, I can do a similar trick, and I can then choose I times sigma I half. So I put an I here and an I here. The problem is that gives me a minus sign here. I don't want that either. But if I choose a minus I, have a minus I here and a minus I there, then the minus sign goes because of the two minus signs. Oh, well, that's not so nice. No, it stays because of the two minus signs. Well, you should complain. I have a minus sign before, and I have two minus signs on the left-hand side. Nothing changes. Minus times minus times minus is minus. That means if I choose this thing, so I take this as a block, and this as a block, comma, and this as a block, so I define the representation like this, then I get precisely this commutation relation. Okay, so this is how you do that. And in quantum mechanics, we often decide that we want this to be Hermitian or something, and then we put an extra I here. Okay, but we can always arrange for this. So I chose this. It's the rotation algebra, so we'll stick to this. This would be the spin representation. And now we calculate the Casimir operator of the spin representation. So this again works precisely like this. So we said the Casimir operator here is minus 1/2 sum I equals 1, 2, 3 of rho xi after rho xi. Again, this 1/2 actually belongs into here. By linearity that works because we need to have the xi's. Okay, fine. So, but now, that's again the general formula. Now I have rho of the spin representation is minus 1/2. So this sum, what is the sum? Well, we have to take the representing matrices. So we have this one times minus I. We have minus I 0, 0 squared. That's right, no? And we have plus, it's this plus from the sum. We have 0, 1, minus 1, 0. No. Okay, I mean, anyway, the overall we have minus I times minus I is minus 1. It's like this. Well, it doesn't matter because there's a square. And the final one is minus I on the diagonal squared that we have to evaluate is minus 1/2 times. Okay, what is this? This is minus I squared is minus 1 minus 1. Agree? Should be. Plus, now this guy squared is this times this is minus 1. Hang on. This times this is minus 1. And then I have this times this is again minus 1. Is that right? Yeah. And then I again have over here, this squared is minus 1 minus 1. Ah, exactly. So this is in total. The minuses all go out and cancel this one, and then there is a 3 everywhere. So it's 3/2 of the identity. Agree? I think that's right. It's 3/2, okay? And hence, the C rho spin is 3/2, or as we like to write it, 1/2 times 1/2 plus 1. Does it work? Well, of course it works, because the algebra has still dimension 3, and the representation space is now 2-dimensional, so it's 3/2. It's, of course, the j times j plus 1. Okay? No? Ah, this is, okay, hang on. So yeah, that's right, that's right. What's wrong with our factors? So here the factor was right. Ah, of course, I took the sigma matrices, and I should have taken the sigma half matrices. But that gives me a factor of a 4th now. Okay, so I should have taken the sigma half matrices, but that says I have an overall factor by 4. That doesn't make it much better, because now I have again a factor 1/2 wrong. Oh dear. J plus, so obviously, yeah. Okay, look. We have a mismatch between the physics and the mathematics definition. Because if this was the spin 1, the vector representation, the number should be 2. J times j plus 1, j equals 1 being a vector would be 1 times 2, 1 plus 1 is 2, but I have this here. So there is a difference between the physics and the mathematics definition. So I claim this result is 3, well, it is 3/8. I cannot change it. This is 3/8, and it is not j times j plus 1, because in the vector case it wasn't either. There is an overall factor of, so in the vector representation, the physics result I have here is a factor of 2 of this, and here also the physics result is a factor of 2 of this, namely 3/4. j times 1/2 plus 1. So this is just a mismatch. So you'd say in physics, okay, let's have this here as an explanation. And I think it's really true. I mean, this is not just, okay, I think it's really true. So the point is that the Casimir operator in physics is defined as twice the Casimir operator we defined here. There's an overall factor of 2. Yeah, and we know this because in physics we take the j squared. Don't you see this? In physics you take the 1/2 over here, so you times 2, and you say it's the j vector squared, meaning the representation of this guy squared, there is no factor 1/2 that goes here. So this is the right mathematics result because you want to have the dual base, well, the psi dual bases on the same space with respect to the killing form in order to make the whole thing basis independent. And how we define it in physics, if I changed bases, I would get a different Casimir operator, which is not good. So that's actually the better definition here, but it relates to this like that. Yeah?
What about the dimensions?
Well, this is C2. This is, we treat this all as complex dimensional representation spaces. Also, this one could have acted on C3. Okay, so I need to take a step back and look from your perspective. That seems to work better. So interesting. Interesting. I don't know. Yeah?
Should it be 3 over 2 or 3 over 4? So we take the complex or real dimensional C2? I don't know.
No, but the factor is 3/8, isn't it? So it's the 1/2 from this definition, and then I take the minus I sigma I tralalala matrices, and I square, and then I have the 1/2 factor becomes a 1/4 from the squaring. This 1/2 is there by definition. Here I always get something of the type minus 1 is 3, it's minus 3 up here. I mean, yeah, if it was a 3 over 4, I'd say, yeah, it's the complex thing counted up. I'm a little confused, I must admit. I'm sorry, I don't get the algebra straight. Unless you see it now, I need to think about it.
Why do we need the 1/2? We needed it on the other side because then 1 came out. So
Well, no, we need it here.
yeah, but do we need it here as well? I don't know if we need it here because if we...
Yes, because this has to do with... Okay, so you say we chose the basis. Yeah. You absolutely think that sounds absolutely right. So we said that in the definition of the omega rho, which is the sum of I equals 1 to dim L of rho of xi after rho of xi I. Aha, very good, Benedict. Thank you very much. We said that the k, that these guys here are such that xi with xi j is minus delta ij. That was the correction because of the compact Lie group. And but of course that depends on this row. That depends on this row because this is the trace of rho of xi after rho of xi j. Aha. Okay. The plot thickens. So if you then use these guys in the spin representation, of course, because of this business here and using these matrices and so on, you of course get a different factor by which the psi j's, well, if they're anyway collinear to the xi's, the xii's, but then you get a different factor here that you need to use in order to make this work. It's an excellent problem sheet question. Okay, I'm sorry, but thank you, Benedict. It's an excellent observation. It's not always the same way you construct the xii's if this is the xi. I was deluded by saying, well, it has just to do with the Lie algebra elements. Yeah, but it's with respect to the k row, to the killing form with respect to the representation. Then you have to adapt this. So this factor here is in question. And it's now entirely clear to all of us that this factor here is, well, so I have a fourth here. So this one half goes, this one half goes, there's a 3. This one half goes, so it's a 3/4, but it must be 3/2. So it's everybody agrees that it's very likely a factor of 2 that you have here, so that you get 3/2. Okay, but now I should make no further guesses here. Just calculate, but that's the origin of the trouble. Okay. Good, excellent. So so you see that different representation spaces, at least if they differ in their dimension, are labeled by different numbers in front of the Casimir operator. All right. Good. And hence we say a particle has spin 1/2 or a particle has spin 1. You can act on any representing vector and it yields the same value for the Casimir operator. So I still maintain that this factor of 2 between mathematics and physics still remains, but the other comment is of course important as well to clarify the mismatch in case of the spin Casimir operator. Now, let's talk about representations of a Lie group. So now turn to Lie groups. Definition. Let G with the blob be a finite dimensional Lie group, then a representation of the Lie group is a map. Now let's call it capital R, and it takes a group element, not an algebra element, it takes a group element and it maps it to, well, not the endomorphisms, but almost to GL over some vector space. So again, the V is some vector space. Okay, so very similar idea, but the GL is of course not the end V, it's a little less. What is GLV? Well, we had it in a special case over C to the N or R to the N. GLV is the set of all linear maps phi from V to V, so I should say phi in the endomorphisms. Okay, but there's an additional condition, and the condition is that the determinant of phi be non-zero, or in other words, then the endomorphism is invertible, that it be invertible. Okay, so there's this restriction, and so this is a map, so such that, so before I write this warning sign, such that if you represent a group element G1 as a general linear map on V, as an invertible, so as an isomorphism on V, and then you use the composition on GLV, because obviously GLV has a composition, and the composition of invertible maps is again invertible, so the circ is closed over GLV. Fine. So you can do RG1 after RG2, and you again land in GLV, and you already guess it, you require compatibility with the group law by saying you could have also first blobbed the two group elements with respect to the Lie group operation, and only then have it mapped over here. That means nothing different but that the circ on GLV mimics what the blob does on the group. And of course, the way the map acts here is important. So that's a representation of the Lie group. So it looks very similar. Okay. Now, examples are in order. So now take as the Lie group, you take SO2. Okay, SO2. And well, you have to use a chart and so on, because the manifold SO2 as a manifold, so as a differentiable manifold, this is S1. So the circle is the manifold that underlies the SO operation, and of course the multiplication on SO2 is moving vectors, well, moving points along the circle. Okay, we know all of this, and you can choose a chart where S1, well, a chart U that lies in S1 that goes to, well, let's call this the angle map that goes to the angle of U lying in R. So it's a one-dimensional manifold, and the angle, well, let's not be childish, so this is called the phi. Phi is called the angle. And you know that if you have S1, you have to take out some point, okay, and then you can, well, let's say you take out this one, and then you can, in a sense, intuitively take this angle, but you cannot cover all of it, because then here you wouldn't be open. Anyway, you can do this, and then you can represent, you have a representation, well, not on the entire group, because you choose coordinates to write it down, but on this U, you have a representation into, I'm sorry, I'm confused. Ah, yeah, you have a representation into GLR squared. So you have a representation space R squared, and it works like that for the group element that corresponds to this coordinate phi. So you take, so I should have called this anyway the angle map. And so then you take the angle map inverse of phi, okay, and that's then obviously an element in the group. And to this element in the group, you associate the matrix. Well, you can represent this by a matrix: cos phi, sin phi, minus sin phi, cos phi. Okay, and you can check that first adding angles here is of course the same as doing compositions there at the end of the day, because of the laws, the addition theorems for cosine and sine. So I claim, so this is the R, so I claim that R of the angle inverse of phi 1 plus phi 2 is the same as R of the angle inverse of phi 1 after R of the angle inverse of phi 2. And hence, this is a, and this angle inverse I only need in order to represent the elements from some chart. This is just more complicated on groups. But if you think about it, you'll see this is very simple. Okay, so we have a representation of S of the group. I'm sorry, it should be a capital SO. I treated it like that, but it's a capital. Have a representation of this group on R2. And this is usually how you first meet it, but it's a representation of this Lie group. Okay? And there's another important example, and that answers again the question, are there any non-trivial representations of a Lie group? And you can define the following. You can construct the adjoint representation, but you say, hang on, the adjoint representation, that was something on the Lie algebra. We're now on the Lie group, and if you're on the Lie group, the adjoint representation is something different, and one usually writes it with a capital A, whereas the adjoint representation on the algebra is written with a small a. They have the same name because they're related, but this is a priori different thing. This capital adjoint is a capital representation on the capital group rather than the small adjoint being a little row on a little algebra. Okay, so construct the adjoint representation. That goes in 2 steps. So first you define the adjoint map that goes by the name capital ad sub G. Now the G is not a Lie algebra element, but the G here is an element of the Lie group. What is ad G? Ad G eats an element in the group and spits out an element in the group. Obviously there's no linearity of any kind here. And how is it defined? Well, it's defined that ad G acting on some element H of the group is defined as G, H, G inverse. And what is between these objects? Of course, there is the blob, the group operation. Now, this seems a little extravagant, this kind of definition, but you can nonetheless make it. It's not a left translation. It's a left translation with L and the right translation with G inverse, one after the other. Okay? So, yeah, anyway, I said it. That's the adjoint map. And the adjoint map has one fantastic property, namely note that the adjoint map acting on the identity yields G, E, G inverse, leads G, G inverse, yields the identity. So the adjoint map keeps the identity where it is. Why is this great? Interesting, since if we consider the push forward of this adjoint map, so you have the ad G with respect to a group element, and of this map you consider the push forward. What does that do? Well, you consider it at a point, and it goes from a tangent space of the group at a certain point, and I like to choose the identity. Why? Because that is where our Lie algebra lies. Okay? It goes into the tangent space at another point, namely at the point ad G of E. You remember? The push forward takes you to the tangent space in the image, but at the point where the map acted on that base point here. Aha! But I just showed you that this is the identity again in case of the adjoint map. So what does that mean? The adjoint map, defined this way, has a push forward that is a linear map by construction between the tangent space at the identity to the tangent space at the identity. Ah, we know that guy. That is the Lie algebra of G. Well, it's at least isomorphic to the Lie algebra on G. Okay? That's the tangent space at the identity. And that means we have here a map that takes you to this ad G, if you provide the G is a map from G to G. Hence, I can look at ad, and ad is without the G down here, and ad takes you from G to the GL on what vector space? Well, on the vector space at the Lie algebra of G, so I can write it as TEG, okay, where the G is mapped to the add sub G, because add sub G, to the add push forward, add G push forward, because that guy lies here. Well, you have to show that it's invertible, but that's not so difficult because this guy is invertible. Obviously, it's add G inverse is the inverse of this, and obviously, so you can go back here as well. So, hence this is true. And what did I show by this? I showed that there is a map that takes you from the group into the general linear group over the Lie algebra. In other words, you can always find a representation of a Lie group on the vector space V given by the Lie algebra. So you could find a representation of the Lie algebra on the Lie algebra, but you can also find a representation of the Lie group on the Lie algebra. A Lie group representation, and that is why this is also called the add G. This is, again, if you have no fantasy, if you just are handed a Lie group and you know about the Lie algebra, you know, oh, with a group I always have a vector space that comes with it, the Lie algebra, the vector space underlying the Lie algebra. You can say, okay, why not try to find a representation that represents the group exactly on that vector space that comes with it, and the map that does that is this add map here. That's the adjoint representation of the Lie group. All right, so are there any questions so far? Okay, fine. So we discussed the representations of finite dimensional Lie algebras. We discussed the representations of finite dimensional Lie groups. And next time, finally, we'll come to the point. So we're down there on the Lie algebra level for quite a while. How do we go back from the Lie algebra level back up to the group? And can we hit the entire group? The answer is generally no. Okay, but there are kind of some interesting facts that one uses very often in this going up. And this going up is called the exponential map. It's a concept from differential geometry, but on Lie groups, these exponential maps have very nice properties, even nicer than they have on normal smooth manifolds, and we'll study them next time. Thank you.